Here's sac213n4. It consists of a circuit in which the resistor represents a computer being powered by a 12-volt power supply. At what I'll call time zero, the 12-volt power supply fails. Think of that as disappearing. At which point, of course, the voltage across the capacitor is 12 volts, V0, because up until that instant, its terminals represent the same point, electrically speaking, as the terminals of the seat of EMF. From time zero on, the capacitor discharges through the computer, our resistor in this circuit. And we want to design this system, in other words, choose the capacitor, so that it takes 4 minutes for the voltage across the capacitor to drop down to 9 volts. So during that 4 minutes, the computer will continue to operate, and whoever's using the computer has time to save their files, save their work, and shut down the computer properly. But the plan is to find the capacitor that you need to make it so that it takes 4 minutes for the voltage to drop down from 12 volts to 9 volts. Okay. Go ahead and draw that circuit as it exists after the power failure, when the power supply is out of the picture. This was 520 ohms. The capacitor C, with V0 being 12 volts, and V at 240 seconds being equal to 9 volts. Okay, the voltage across the capacitor, which is also the voltage across the resistor, is given as a function of time by this expression. So it dies off exponentially with time. And what we're supposed to solve for is C. The resistance is known. Time is going to be our 4 minutes, or 420 seconds. V0 is 12 volts, and V is 9 volts. So let's go ahead and solve that for C. I'll divide both sides by V0. And take natural log of both sides. Now multiply both sides by C and divide both sides by this natural log. And there's still an R down here. Okay, and C is minus 240 seconds divided by 520 ohms times the natural log of 12 volts divided by, I'm sorry, it's 9 volts is the final voltage. And then divided by the initial voltage, V0, which is 12 volts. Then we plug those values into the calculator. And I get 1.6 farads. So this is a design problem, right? An engineering problem where the engineer has to find out what capacitor needs to be used, and we find it's a very huge capacitance. You get a big capacitor that you use in the lab. I think it's 4,700 microfarads, 4.7 times 10 to the minus 3 farads, or 0.0047 farads, I believe. And that's a pretty good-sized capacitance for a circuit. This is just huge. Physically, that would be a large capacitor and very expensive.